I'll start this recording. Have those recordings been working out for you guys? Maybe, I don't know, in case you missed class or whatever. I don't know. So everyone has a copy of what I almost finished. I started from the bottom, now we're here. No, but I did. I started from the bottom. I did chapter 11, then chapter 10. And then I was running out of time, so I didn't get through chapter 2 and 1. So, well, sort of. Mine goes from chapter 1 to chapter 7, so it's not very helpful, actually, now that I'm looking at it. But like I said, those printed funny. But what I want to do today is just go through this whole document and just kind of highlight things to keep an eye out for, right? I mean, first things first, your grades on Moodle right now, they're not out of 100, right? They're out of 70%, right? And so a good skill to have is to know what your grade is, especially because at the end of the term, I'll send out an email being like, hey, your final exam grades are posted. Oh, you guys know them already. But anyways, just you have to check that these grades are what you expect them to be, right? And so you have your grade for your group assignment, your quiz 1, your group assignment 2, and your quiz 2, and then you'll have your grade for your final exam. So what you should be doing is you should just keep a tally here of your grades, right? And this should be as a decimal. Okay. So let's say I got, well, you all got the same grade, but I can't remember what it was for group assignment 1. 33 out of 35. Okay, so 33 out of 35. Let's see here. Whoops. 33 out of 35. 94.3, so 0.94. I mean, you could keep all your decimal places if you want. I'm going to round up to 3. Okay. And then what you're going to do is you're going to multiply that by 15, because that means that that group assignment counted as 14.14 out of 15 of your whole grade, right? And so what you have is 14.14. So at that point, right, your grade would have been the 94.3, right? But as we keep going, you're going to take this grade and divide it by your cumulative grade. You know what cumulative means now? You probably did before too, actually. It's just a word, guys. So then you keep adding, right, your percentages, and then after you've done your final exam, well, then that grade is going to be, that doesn't really make sense, actually. There's a separate, you need your cumulative grade times weight. That's what you need. You need a new column in there. Ugh.
There's no way to make Moodle do that?
Moodle does it, but you should be able to check it to make sure that Moodle does what it's supposed to be doing. Here's my new column. Voluptuous. For your cumulative grade times weight. Sloppy, sloppy. Right. So yeah, Moodle does do that, but you should absolutely check to make sure that it is calculating correctly. We can't just trust the machine, guys. for humans. Okay. All right. So, and then you would go so on and so forth. Your cumulative, bless you, your cumulative grade times weight, right? You would add up how much of your grade you have at that point, and then you could find it as a percentage. Right? Your total grade on Moodle right now is this one here, right? So you would divide it by 70% to see where you're actually at, right? Or divide it by 70. And then you can do fun things like, how much do I need on the final to get this grade? How much can I get away with on the final to pass? No, you guys need more than pass, but you get the idea. Okay. So just a good, I guess, life skill, school skill. Not really a life skill, I guess. Well, it is. And it's math, so I feel like it's appropriate. All right. So here are all the things I didn't get to. So what I'll do is I will obviously finish this list and then I'll post it on Moodle again. But at least I just wanted you to have a printout of most of the things, right? So even though some of the things aren't filled in yet, there's a lot of information in here. And because we're going through it together, thought it might be helpful to have a printout. Okay. So what I did was I went through and I did your final exam. Okay, I'll tell you, I got a couple wrong, but that's because the answers are wrong. And two, because I didn't read the question properly. So I will change those for you guys so that they're good. But otherwise, I think they're very reasonable questions. Again, just like the other tests, they're from a test bank from the textbook, right? So we have seen these types of problems before. In fact, there's a couple of repeats. Fun, right? Redemption round. So, so today we're just gonna go through and just kind of do a complete overview. You're telling me we could have done this course in 3 hours? Time me. I guess I only have less than 3 hours now. Ugh. Okay. The levels of measurement, chapter 1, I do feel like you guys have a really good handle on by now, right? And so we talked about well, quantitative, qualitative data, right? Categorical, numerical, depending on what type of variable we have, right? That's going to dictate what type of analyses we can do, right? If we have a numerical variable, then we can do things like the t-test and Anova, right? So let's see if I can squeeze that on here. Let's us do t-tests, Anova, Levine's test. Oops. I'm going to change the size of this here. Levine's test, okay, etc. Right? These are any tests for means or standard deviations. Okay. Whereas if we have categorical data, right, or qualitative data, right, then it lets us do, shouldn't be apostrophe, should it? Lets us do chi-squared tests, chi-squared test, Fisher's exact test, McNamara tests, Fisher's exact. Let me sit down, this is too messy. It won't help, but it'll feel better. Fisher's exact test, McNamara test, It's another one. Oh, should add correlation to the numerical. Correlation or correlation here, depending on what kind of data we have. Anyways, that's plenty for now. Okay. So depending on what type of variable we're analyzing, right, that's going to dictate what type of tests we can do. So then we have to keep track of our independent variable and our dependent variable, right? The dependent variable is also known as the response variable, right? This is the variable of interest. Also called the outcome variable. Whereas the independent variable is usually just the grouping variable, right? Usually a grouping variable. Doesn't have to be, but usually. Okay. If you've got a scatter plot, we said that, okay, we're going to put our dependent variable on our y-axis and our independent variable on our x-axis. Now we're heading into our nominal ordinal interval ratio. I still can't keep these straight, the interval ratio ones. One has a true zero, one has a fake zero. I can't remember which one's which. But anyways, so I'll whittle that down and I'll post it later. How about that? How about that? All right. We could look it up in the textbook just as well. And I think you guys know it better than I do. Because for me, what I do is I've just grouped these two, nominal and ordinal, as categorical, and interval and ratio as numerical. And then I just kind of leave it be. Continuous data is measured on a continuous scale, right? So things like speed, weight, even weight, right? The reason that we're measuring to maybe 1 or 2 decimal places is not because weight doesn't go to 4 decimal places, it's because our measurement tool can only go to 2 decimal places, right? So if you think about it that way, so we've got this continuous scale, right? Whereas if we've got discrete data, then we've got these classifications, things like age. I mean, unless you're really young, you would probably say, oh, I'm, 3.5 or something like that. But how old am I? 33 and a half, let's say. I don't know. For the longest time, like probably from when I was 27, I told people I was 30. And then after that, I was like, well, now I am 30. And then I was 31, and I was still 30. So I've been 30 for like a long time now. So mostly because I couldn't wait to get to 30. But now I'm like, hold up. So anyways, that's neither here nor there. Well, it's discrete data. So one new one, because these are probably familiar, right? I just stole them from all your study guides. I compiled them, kind of added to them. And so one thing that I added fresh that you might want to keep an eye out for is that we haven't talked about is the Likert scale. Okay, a Likert scale you might have heard about is just a rating scale. So if I give you, so how bad is your pain on a scale of 1 to 10, that's a Likert scale. Okay? One thing to keep in mind about the Likert scale is that because we can talk about the average pain score, for example, right? It makes sense to talk about the average. It's a numerical variable, right? And so even though it's discrete, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? But it's still going to be considered a numerical variable. Okay? So I added that one because you might find it helpful. Maybe. Okay. I know chapter 1 notes are very sparse, but any questions? Well, yeah. Chapter 2 was one of those fun sections where we're just talking about, okay, how do we present data, right? Depending on the type of variable that we have, again, right? A scatter plot we know is something that looks like this, right? Where you've mapped your dependent variable to your independent variable or against your independent variable. A line graph is not something that I'm too concerned about, right? But you've got, can I zoom in here for a line graph? Right, so you've got these points representing activity over time, and then what I'm gonna do, a line graph just connects these points. Oh, should connect them properly to show how things changed over time. Right. And we use chart and graph interchangeably, right? So a bar graph or a bar chart, right? It has a nominal variable on the horizontal axis, right? Meaning, so we have our categories. In general, I would even use it for ordinal variables. I don't really care. In fact, you know what? Do what I want. I'm going to change this from nominal variable to just a categorical variable. I know the textbook went ahead and said, okay, for an ordinal variable, you're going to use a histogram, but I disagree with that. So, and you guys are mine. So, okay, but so we've got this categorical variable on the horizontal axis, and then the bars are just representing the counts in each category. As an example, the frequency goes on the y-axis, and then let's say male and female, those are our two categories on the x-axis. Maybe it looks something like that. Kind of a wonky bar. No? A histogram has a numerical, and then I'll put in brackets or ordinal, but I want you to focus on the numerical variable on the horizontal axis. And then again, it has the frequency, and it lets us see the distribution of that numerical variable, right? So it's going to be essentially a bar graph, but So we've got a frequency, and then if we talk about something numerical like height, for example, then we've got the counts in each group. Something like that. If I'm looking at this, even though I just drew it, how would I describe the shape? Just kind of skipping forward to that, right? I would say this is an approximately normal distribution because we've got this kind of bell shape. Right? We're very flexible with how it looks depending on our sample size, especially if we have a small sample size, then we're very flexible with how our normal distribution looks. A lot of our analyses hinge on having a normal distribution, right? So t-tests, you have to have a normal distribution, ANOVAs, correlation, right? And so a lot of these things kind of hinge on having a normal distribution. So I often just say, oh, it looks approximately normal with the exception of this and this, right? If it's not quite. We always argue that you have a normal distribution. And then a frequency distribution is just a summary of the numerical counts of the values, right? And so usually a table, right? Or it is a table. Presented as a table. And one thing that I would add in here, right, is our cumulative frequency distribution. Speaking of our grades and things, right? So I'm going to add in here the cumulative frequency distribution. That's where we add up the frequencies from the previous rows, right, until we've reached our whole sample size. So I feel like she probably has a better explanation, but here we go. Each row has the sum of the current row and previous rows. You will be given a frequency distribution, right? And asked to pick, you know, a category that satisfies some criteria, right? Just reading this frequency distribution, and then use it again to figure out what the cumulative frequency is, or the cumulative percentage. But that works the same way, right? So you'll have to work with a frequency distribution. Any questions about that? Oh. Descriptive statistics. Got no time either. Descriptive statistics in general are just any calculation that we have done on our sample, right? Things like the mean, the median, the standard deviation, the variance, right? Those are all descriptive statistics, things that describe our sample, because a statistic is from the sample, right? Whereas a parameter is from the population. In fact, why not? Let's add that on here. It's not on the final, but I feel like it's good for completeness. A parameter is a measurement from the population, whereas the statistic is a measurement from the sample. Notice P and P and S and S. This is clearly where I got interrupted, that's why. The mean is the average. It only applies to numerical data. Right. The mean is the average, and it only applies to numerical data, and it's a good measure of center for a normal distribution, right? So for normally distributed variables. So it's the best measure of center for normally distributed data. The median, right, is the central value, and we use the boop, boop, boop method, right? And so we sort our data and then we kind of work our way in, right? Or you can use Excel or whatever software you want. It'll be able to calculate the median for you if you have large data sets. And so the median is the central value and it's going to be the best measure of center for skewed distributions, right? Because it's the one that holds steady. So it's the best measure of center for skewed distributions. And then our mode, right, is just the most frequently occurring value, right? And so that's not very helpful, except if we have a categorical variable, right? Then we want to say, okay, well, if you have the most females, for example, that would be your mode. Okay? And so mode is the most frequently occurring value I guess it's the best slash only. It's the best measure of center for categorical data. These kind of work in cascading ways. So if you have a normal distribution, then you can use the mean, the median, and the mode. They'll all be the same, right? Whereas if you have a skewed distribution, then you can use the median and the mode because they'll be the same. And if you have categorical data, you can only use the mode, right? And so they just kind of shrink down as you move through them. Yeah. Any questions? All right. Standard deviation, just by definition, is the average distance. The values in a distribution are from the mean, right, or from the center. From the center, the mean. And it's the most common measure of spread for normally distributed data. And so, and then the variance is just the standard deviation squared, so we could just as well use that, right? Whenever we can use the standard deviation, we can also use the variance and vice versa, because they're just the square and the square root of each other, right? And so if the standard deviation is S, then the variance is S squared. Did not clean these up. Chapter 3. I know. The normal distribution, it is a probability distribution, but the key thing is that the mean, the median, and the mode, they're all equal, right? Because we've got this symmetric bell shape. And so it's going to look like this. That's pretty good, I guess. If I zoom out, it looks great. So that's a normal distribution. And then the key here is that the mean, the median, and the mode are equal. Should just use one highlight. There. Okay. So then a skewed distribution, right, is an asymmetrical distribution, and it's a little bit counterintuitive because it's always skewed in the direction of the tail, right? And so there are two questions where you have to think about, okay, one where it gives you the mean and the median, and you have to figure out, okay, well, what's the distribution here? And then one just gives you the scenario, and you have to figure out what the distribution might be, right? And so what happens is, I'm going to put this down here. Wait. Though fun, I'm not going to do that. There. So if you've got a skewed distribution, it might look something like this, right? This is skewed to the right because it's always skewed in the direction of the tail, right? And I'm positive it's, yeah, that's on here. Distributions are skewed in the direction of the tail. So a negative skew would mean that the tail is in the negative direction. And another thing is that the mean is always pulled towards the tail, right? Whereas the median holds steady, and that's why we use it as the best measure of center for a skewed distribution. Okay, so what that looks like is, well, this is skewed to the right, or we could call it a positive skew. And so our median would still be here, kind of doing a good job at measuring the center. And the mean is pulled in the direction of the tail, which is also on here. In a skewed distribution, the mean is pulled in the direction of the tail. Bless you. So then on the other end, this is skewed to the left, or we could call it a negative skew. And the median would still be hanging out here, doing a fairly decent job at telling us where the center is, but the mean is pulled in the direction of the tail. So you want to keep a handle on that. The range of the data, it's just the difference between the maximum and the minimum values, right? So nothing crazy. And quite frankly, it's not going to come up. So, okay. But you will want to keep a handle on these ones here. I guess I could draw the normal distribution on here as well. That's supposed to be a normal distribution. Mean equals the median. And if we want to throw the mode on here, it's also equal to the mode, and the median is usually approximately equal to the mode for skewed distributions. Okay. But the ones to keep a handle on is how the median is related to the mean. Questions about that? No? Bless you. So, and just as a side note, you're still more than welcome to stop by and we can go through your quiz 1, quiz 2, right? And so just to make sure that you've got any questions that you got wrong under control. Because especially these guys, they're a little bit slippery, right? Content validity, predictive validity, blah, 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 blah. So let's just talk about them. So feasibility, I think we all understand like how reasonable, how doable is this study, right? So is it possible from a practical standpoint? But then the other one, so validity is just the general kind of umbrella term for how accurate is your data, how valid is your data, right? And so I feel like, was it on test quiz 1 or quiz 2 that there was a question about, okay, so you did a survey with I think Hispanic mothers or something like that, and turns out none of them spoke English. So what did that impact? Impacts the validity, right? Because if they're not able to complete the questions properly and they're just picking random answers, presumably if they don't know English, then your data is not valid. And so you have to keep that in mind, right? Content validity is basically when your survey measures what you think it's going to, right? How valid is this, is the content of your instrument? Your instrument is typically your survey. So when the survey used is designed to accurately measure the concepts under study, right? So then all your content is giving you valid information. Convergent validity, I should move next to divergent validity, right? But convergent validity is, so you've got this survey that you've developed, and there's big business in developing surveys, right? So you've developed this survey, and you're saying, yeah, it's able to predict these things, right? And then there's another kind of well-tested survey out there, and you're getting the same results, right? Your survey is getting the same results that you would expect to see with this presumably more expensive survey, right? So that would be convergent validity, where things are just converging and your survey instrument converges with the results of the other instrument that is already considered valid, right? So if that's valid and yours are converging, then yours is valid, right? That's convergent validity. Skipping to divergent validity for a sec, right? That's the opposite direction, right? So now your results, you're expecting them to be opposite of this established survey, right? And they do, right? Because they're diverging. Okay. So because you're expecting the opposite results, that would be divergent validity if you're actually getting opposite results. Predictive validity is, okay, so you've developed this survey and you're saying, okay, well, if you answer these and these questions like this, you're more likely to do this 10 years from now, right? I know, very vague. Sorry, guys. Right, but it's able to predict something in the future. So when the instrument used accurately suggests future outcomes or behaviors. Reliability is the consistency or the repeatability of your survey instrument. And so one thing that we have to keep in mind, right, the three main factors that relate to reliability: stability, homogeneity, and equivalence. Probably commit those to memory, those three. Stability, homogeneity, and equivalence got separated because I threw in Cronbach's alpha. Okay, Cronbach's alpha is separate from our hypothesis testing alpha, right? That's why we call it Cronbach's alpha. It's not just our Joe Blow alpha, right? And so it's going to be a measure of internal consistency, right? And so if you need a number to communicate how reliable your results are, you usually use Cronbach's alpha. Okay? So Cronbach's alpha is a number to communicate the reliability of your instrument. Oops. I guess we could just say the reliability. I'm going to leave it at that. So it's a number to communicate the reliability. So now, talking about these components, right? The stability, the homogeneity, and the equivalence, and they're all basically the same. Stability is just how stable is this measurement, right? So if you're giving it basically the same answers, right? Are they classifying them as the same, or is it saying, whoa, these answers are so different? Homogeneity, right, is just how, can I say homogeneous? Right, so how the same are all these things, right? And so a multi-item instrument, so basically any survey, right? Are they consistent with one another, right? So are you asking consistently about the same thing? And equivalence is just how well multiple forms, right, give you the same results. So these are all basically the same thing, right? Not a huge difference between them, but they all factor into reliability, right? And so reliability is not really that different from any of those three, right? It will do this to show you that they're down here. There. Any questions? Feels like so long ago that we did that stuff, right? Crazy. Sampling methods. We talked about all these different sampling methods: cluster sample, stratified sample, systematic sampling, convenience sampling, simple random sampling, quota sampling, blah, 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 blah. I'll put the definitions on there. You've got them, I'm sure of it. I'm sure there's flashcards somewhere. I know you're kind. So you know these. The main one that, of course, I'm concerned with is just a simple random sample, right? Because that's our most basic probability sampling, right? And so what I have to add on here is probability sampling, right? This is the most basic form, hashtag basic, no, most basic form of probability sampling. Probability sampling is just if it was randomly selected, right? So probability sampling I'll just say it's random, right? Whereas any sampling that wasn't random, right? Things like convenience sampling, I'd say even systematic, but I'll have to check. Not really random, but sort of. Convenience sampling is non-probability sampling. Pardon? Quota as well? Great. Thank you. Got my fact checkers. It's like, I need you in my ear though. Okay. So, like I said, I'll clean these up, but these are just definitions. And I think there's one or two questions where it says, oh, a nurse researcher wants to do this. And so she collects her study or her sample this way. What type of sampling was it? Right. And then you just have to pick which one. Anyways, leave it at that. You guys can do it though. Any questions about that one? Pretty bare bones. Don't worry, we're getting into my meat and potatoes here. So, Chapter 6, we just kind of used to introduce things about hypothesis testing, right? And then we spent the rest of the chapters going through different types of hypothesis tests, right? And so this is all going to feel kind of like, oh, so what did we learn in that section? Because then we really talked about it later in future chapters as well. But just in general, right, a hypothesis is just some research idea that you have, right, and that you want to test and that it can be tested, in general, our null hypothesis is that there's no difference, right? There's no difference, there's no association, there's no relationship. And what I've done later on, as you'll see, is for each of the tests that we're doing, I've given the null hypothesis, right? That would be appropriate for each of those tests. And so, but the key thing here is that there's no difference between these things. And then the alternative hypothesis is usually the relationship that you suspect is there, right? So it's usually the thing that you think is going on, right? But what we have to do, right, is we have to do all our testing assuming that there's no relationship until our sample proves otherwise. Right? And so our alternative hypothesis is just that there is a difference. There is an association, there is a relationship. Yeah. Statistical significance is when the difference you observe between two samples is large enough that it's not simply due to chance. How do we talk about it though? If you reject H0, you have statistical significance. Clinically, we've been calling it clinically significant, right? So in order to be clinically significant, right, our result has to be statistically significant, right? There has to be a difference for us to say it's clinical significance, but also has to be clinically useful, right? And so you've seen that on quiz 2, I know that. And yeah, it's gonna come up again, right? So you have to keep track of, okay, so, but in order to be clinically significant, right, has to be statistically significant and clinically useful, right? And so this was one of those where, okay, before you rush out and suggest changes that might cost a lot of money, right, then you would have to make sure that it's clinically significant, right? Make sure that it's statistically significant and clinically useful. Right? Then we got into, oh, I didn't bring your formula sheet. It's all right. I guess not really. Sensitivity, specificity, positive predictive value, and the efficiency. Those are all on your formula sheet. And your formula sheet is not going to change from quiz 2. And I think you guys got yours, right? And it's posted on Moodle. In fact, I'll maybe go grab it. Khan Academy. What a guy. I have to teach sign law tomorrow, and I'm like, there's got to be a better way to say it. And of course, Sal Khan's got it under control. Bless you. Where did I put it? I put it in your quiz 2, probably.
Do we get that on the final or do you bring it?
No, I'll print off a fresh one for you.
Do we need the chi-squared things or the tables?
No. So you don't need any tables. You don't need to calculate any chi-squared or any standard deviations. So you're home free. But this is where your formula sheet will come in handy, right? It's going to be when you have to talk about sensitivity, specificity, PPV, negative PV or NPV, prevalence, efficiency. Only some of those are on the study guide, but I mean, in general, they're all on your formula sheet, right? And so what you'll have to do, though, is you can derive the definition of each of these based off of the calculation, right? And so if you need to know what the specificity is, so I think that was the definition that we're talking about. At least that's the one we're starting with. Well, specificity is D over B plus D, right? So D is the count of those who test negative, who should test negative, right? Because the disease isn't there, over everyone who doesn't have the disease, right? And so it's the specificity is the percentage of, or I guess proportion of those, because they didn't multiply by 100, doesn't matter. It's the proportion of those who tested negative that should test negative, all right? So here we go, let's. So then was specificity here, the probability that a well subject will have a negative screen, right? The probability of a true negative, right? So you can match that to the calculations, right? The calculations give you all those definitions. You just have to figure your way to them. Okay? So same thing, sensitivity, specificity, PPV, efficiency, all of those, right? Those are on your formula sheet. And we've got our true positives, true negatives, false positives, false negatives, blah, blah, blah. Okay. Any questions about those? No. It's all a memory game, but not really, because those are on your formula. So the alpha level, right, is the significance level of a test. And so now we know, and we're very familiar, right, with the alpha level, because if our p-value is less than our alpha level, we have enough evidence to reject H0, and so we found a statistically significant relationship. Right. And so it's all this big. And what you've probably noticed from, well, you probably spent more time on the practice quiz too that I posted, right? But some of those questions were, okay, so they found that there is a difference between these two groups. And so what does that mean in terms of the p-value, right? And the alpha level, things like that. And so it's usually like a multi-phase thinking problem, right? Not just the one-step problem. The key thing here is you always decide your alpha level, right? You always decide your significance level before you do any testing, right? And so it's basically the first thing that you do besides stating your null and alternative hypothesis. So I'm actually going to highlight that. Hey, I didn't say Siri. The p-value, right, by definition, is the probability of seeing something as extreme or more extreme than what you saw in your sample, assuming that the null hypothesis is true, right? So it's hinging on that, assuming that the null hypothesis is true, because we've done all our testing assuming H0 is true until the end where we said, well, actually, what we saw is way too extreme to have happened just by chance, right? So that's why I can reject my null hypothesis, right? The p-value, if we're thinking about a curve that we're familiar with, the normal distribution, then the p-value is the area in the tails, right? The area under the curve is a probability, and so then the probability of seeing something as extreme or more extreme is the area in the tails. If you're looking at both tails, you've got a two-sided p-value. If you're looking at one tail, you've got a one-sided p-value, and we'll go through those a little bit later. And here again, just re-emphasizes, because it's important, right, that we know what to do if the p-value is less than the alpha level. Oh, I wonder if I can find them. Anyways. I'll put some funnies in there when I post it, because I can't remember where I put them. Let me see here. It's important. Not actually. I've got a folder called funnies. Oh, well, here's a, yeah, I may as well show you. That's correlation. Correlation does not imply causation. There's a message with each of these. Anyways, so, but that's not the one I want. Here it is. It's a little borderline, but very catchy, right? If the p is low, then the null hypothesis must go. So now you've got it locked in. See, worth it, right? The number of times that I've marked final exams and I've seen that like scribbled in the corner, it's so funny. I'm like, oh, it works. So anyways. Back to work. I've got more, but oh, I don't know what happened there, but it's probably fine now. Okay. No hands. What is it gonna look? Okay. Let me know if it switches again. Is that where? How do I? Thank you. technology, right? All right, so in case the p-value was not clear, that should kind of help solidify things, right? Or even if you're doubting yourself, as a rule, never ever doubt yourself. You've got it, it's in here. Just trust your gut. Okay, I'm scrolling on there, it's on here. Okay, so if the p-value is less than the alpha level, we have enough evidence to reject H0 in favor of HA. And of course, the alternative is if the p-value is not less than the alpha level, then we don't have enough evidence to reject H0. That's the same as saying that we failed to reject the null hypothesis. All right. The null hypothesis is on here again. I'll clean that up. And same with the alternative hypothesis, but it has more information this time, so I'll probably keep this one. Specifically talking about directional and non-directional, so one-sided or two-sided tests, right? And so let me see if I've got, this is probably the best option. So in terms of a t-test, then if our null hypothesis is, so we're doing an independent samples t-test, right? If the null hypothesis is always going to be that the mean of group 1 is the same as the mean of group 2, right? They're equal, there's no difference, there's no change, nothing going on here. If your alternative hypothesis is that there's a difference, right? Is different, that's essentially a not equal to, making it non-directional. You don't care which side it's going to or which tail it's going to. So what that looks like in our distribution, right, is that we've got this two-sided test. Because I don't care which direction it's going, hence it being non-directional. And so this makes it a two-sided test. Two-sided or two-tailed test. Whereas if your alternative hypothesis is that the mean of group 1 is less than the mean of group 2, right now you're looking at some direction. In fact, you're looking at the lower tail. So this is a a one-sided or a one-tailed test, which is the same for if the mean of group 1 is greater than, but now you're looking at the upper tail. There. Also one-sided or two-sided. One-sided or one-tailed, sorry. Can't talk. Bad day for not being able to talk. Okay. Hypothesis testing, right? Just set of rules that we follow, and these steps will always be the same. And so regardless of what we're testing or what our research question is, right, we're going to state our null and alternative hypothesis. Next thing we're going to do is we're going to pick an alpha level, right, pick a significance level. Then first we have to decide what test we're going to use, right? What test is going to be appropriate based off of our data, right? Do we have numerical data? Do we want to compare two means, for example? Then we use a t-test. Are these groups independent or dependent? That's going to determine our t-test. right? And so do we have categorical variables, right? Maybe a chi-squared test, just like this. Things like that, right? So just figure out what type of test you should be doing, okay? And then do the test, right? So this step 3, changes depending on what type of data you have, right? But you're always going to figure out what test you need to do and then do that test. And then after that, you're going to have the p-value, right? The p-value behaves the same regardless of what tests you've done, right? And so if your p-value is small enough, smaller than the alpha level, you can reject H naught, right? That's always the behavior. And that's your conclusion in step 5, right? Decide whether you have enough evidence to reject H naught or not. One thing that I will point out, right? Our conclusion is always in terms of the null hypothesis. The reason is because we did all our testing assuming H naught is true, right? And so if we're rejecting H naught, right, we can't just say, oh, we're gonna fail to reject the alternative hypothesis. That doesn't make sense because we did our testing assuming the null hypothesis is true. So then our conclusion should be, oh, we were right or we were wrong, right, in terms of our null hypothesis. This can obviously be condensed a little bit, but right, if you're rejecting H naught, then you have statistical significant results, right? Or these are statistically significant. Whereas if you're not rejecting H naught, if you fail to reject H naught, then they're not statistically significant, right? Not statistically significantly different, right? If we're comparing means, for example, these means might be different, but unless we're rejecting H naught, they're not statistically significantly different, right? Or significantly different. Okay. So how I kind of think about it is that, okay, if you said, or if someone asked you, hey, where's Emily standing? Oh, she's over there by the desk, yeah? Probably how you would say, oh, she's over there by the desk, right? Even if I was standing here, right? I'm further from the desk, but you'd probably still say that I'm still standing by the desk. Oh, she's over there by the desk, right? And so this difference is not significantly different, right? And so there can be differences in your data, but your p-value tells you if it's statistically significant. Okay? And so we must rely on our p-value to determine if results are statistically significant. So we must rely on our p-value to determine if results are statistically significant. Statistically significant. Got some repeats on here. It's all right. I'll consolidate. Clinical significance, again, we've already talked about it, right? But hey, it must be important. Have to be statistically significant and clinically useful, right? Don't worry, there are no confidence intervals on the final, but I left it on here for completeness. And confidence intervals, right? We have our sample mean, but we know that our population mean, for example, is not going to be the exact same as our sample mean. So a confidence interval just lets us build bounds around our estimate to figure out what a reasonable range for a population mean might be. But that's all I'll say about that. Oh, type 1 and type 2 errors. I'm impressed you guys got these under control for quiz 2, so that's really good. Right. I'm going to skip ahead to this table that I like to make in my mind, because, and probably just jot down as soon as you sit down for the test, as soon as you're allowed to empty your brain onto a piece of paper. I would probably just jot this one down, because from this table, I can pull out the definition of a type 1, type 2 error, the power, what is the alpha, what's the probability of a type 2 error, what's the probability of a type 1 error. And so all these things we can condense into a table like this. And so in our rows, I've got my kind of decision, right? There's two possible decisions that I could make. I could reject H0 and I could fail to reject H0. I don't know if those are errors or not, right? But I could be making a mistake, because either H0 is true, right? Meaning you shouldn't reject H0. Then if I'm rejecting H0, then I've made a type 1 error, right? So from here, I could say, well, the definition of a type 1 error is incorrectly rejecting a null hypothesis, right? The probability of a type 1 error is alpha. If H0 is false, which means I should reject H0, right? Then, and I've rejected it, there's no error, right? That happens with a probability of 1 minus beta, and that's your power. So the definition of your power is correctly rejecting H0. Right? If I fail to reject H0, I don't know what the truth is, right? But there's always a chance that I made a type 2 error, right? Where I didn't reject H0, but I should have. And that's going to happen with a probability of beta, right? And so your type 1 error happens with a probability of alpha. Your type 2 error happens with a probability of beta. And then, well, we don't really care about this one. If you fail to reject H0 when H0 shouldn't be rejected, that's fine. And it's not a scenario that we talk about that much. Okay. One thing to keep in mind, as soon as you've decided to reject H0, there's always a chance that you're making a type 1 error, right? And as soon as you decided to not reject H0, there's always a chance that you're making a type 2 error, right? They don't cross. So if you've rejected H0, you can't make a type 2 error, because that doesn't come into play, right? And so reject H0, type 1 error, fail to reject H0, type 2 error. Yeah. Any questions about that one? So I think a lot of these things can be traced back to just this table, and a lot of these questions can be answered using this table, right? And so we've seen a lot of questions where it says, oh, so this study found that there was a significant difference in the means between these two things. If they made an error, what does that mean? Well, it means that they rejected H0. If they made an error, it means they rejected H0 when they shouldn't have, right? And so if they rejected H0 when they shouldn't have, they made a type 1 error. And there are no type 3 errors, even though it will be an option, so don't go for it. I like to keep those in there though, or I even put them in, because I want you guys to have easy non-options, right? Can't be that, because it doesn't exist. Type 3 error is one of them. Okay. Any questions about that? Oh. Moving on. So a z-test where it's not going to come up on the final, but z-scores are, right? So z-tests are t-tests, but when we know sigma, that's not going to happen in real life. And so, is it missing a page? No,
No,
you're good. Okay. Okay. But z-scores will come up, right? And it just tells us how many standard deviations we are above or below the mean, right? So if it's positive, we're above the mean. If it's negative, we're below the mean, right? And so what we said was, as a rule, any z that's more than 2 units away from 0, right, plus or minus 2, we reject H naught. Okay? And so any z beyond plus or minus 2 will be considered extreme. And so what that's equivalent to in hypothesis testing is, if it's extreme, we would reject H naught, right? And so now we're making those links here. So this is essentially saying we would reject H naught. So we would have a statistically significant difference, right? Okay. Make sure you slam the door though. Keep them guessing. Okay, so if you know what a z-score or what the z-score is, right, then you can determine if you should reject H naught or not, based off of it just being, as a rule, whether it's beyond 2 standard deviations away. We also have the empirical rule. The empirical rule, I'm going to scoot this down a bit here. The empirical rule is also called the 68, 95, 99.7% rule. It applies to normal distributions. Applies to normal distributions. Right? So thinking about a z-distribution is a normal distribution. That's where we started with these normal distributions. And z is a normal distribution centered on 0. So I'll just put a label down here, the z-distribution centered on 0. And the standard deviation is 1. Oh. What the empirical rule says, and this applies to all normal distributions, but we're just looking in the special case of the z-distribution because it's easier to think about, right? The empirical rule says that if we go from the mean, being 0 for this example, right, from the mean, if we go up 1 standard deviation and down 1 standard deviation, we've covered the central 68% of the curve, right? And so here, I'll use to -1 and 1. This area here is 68%. I guess I should scoot that down because I need to have room for, or up maybe. I need to have room for 3 of these distances. There. I've been teaching this stuff for almost 5 years now, and I still haven't figured out the best way to show this because there's so much information on one graph. But I feel like I'm onto something. So if you move out 2 standard deviations on either end, right, always from the center, you've covered the central 95% of the curve. There was a flickering, right? Okay. Like, good thing you guys are nurses. As good as. Hey. It's all about confidence. And then I'll use a third color because once we've moved out, and this applies to any normal distribution and any mean and any standard deviation, once you've moved out 3 standard deviations, central 99.7% of the curve, right? Meaning there's only 0.3% left to split between the 2 tails, right? And so here, so what does that mean? Now that we have this kind of understanding of p-values and alpha levels and things like that, right? If we're saying that a z that's beyond 2 is significant, right, or extreme, well, if between -2 and 2 is 95, I've got 5% left over, right? That's the same as our alpha 0.05, right? Alpha is 5%. We've got 5% left over. And so as a rule, anything more than 2 standard deviations away, we can reject H0 because our p-value is the area of the tail, is less than 0.05. Whoa. I know. Cool, right? But so that's the reason. Any questions about that? It's a lot of stuff. Okay. There were 2 empirical rule calculations where it gives you the mean and the standard deviation. One, I mean, I used my calculator for it. You'll probably want to use your calculator. One I didn't even use my calculator for because it was so breezy. So, but there will be 2. So things like, okay, if the mean is 4 and the standard deviation is 1, between what values do you expect the central 68% to be between? If the mean is 4 and the standard deviation is 1, well, that puts you at 3 and 5. So then you'd expect 68% of your values to be between 3 and 5. Right. Like I said, it applies to any normal distribution with any mean, any standard deviation. We've just boiled it down to the standard normal, the Z distribution. I guess you could calculate your Z score, but nah. You don't have to. So then we had this kind of random chapter about sample size, effect size, and power. Power, right, we said from our table, if you have a look, well, the power is the probability of rejecting H0 when you should have. Or rejecting H0, or correctly rejecting H0. Yeah. Oh, yes. Stand. You want a break, maybe? I'm blabbing. I have gone for 3 hours and forgotten to give people a break, so you do have to stop me. How about we do I don't know, 15-minute break? Sound good? No. Go break. I'll even there for all right. No, I like it when you guys are talking, but I like it more when I'm talking. Love hearing my own voice. No, actually, I kind of don't listen sometimes, and yeah, kind of a weird thing. Sometimes I find myself talking, but I'm like, what am I even saying? Weird, right? Autopilot, for real. Don't worry, I've checked the recordings, it all makes sense, but really not paying attention. Anyways, all right. So this section was kind of wishy-washy, right? There was no hypothesis testing yet or anything like that. And so we talked about power, we talked about the effect size, which later, right, we found out that the effect size is actually the correlation. And so if we've got the effect size ranges figured out, then we also know the correlation ranges, right, for what's weak, what's moderate, and what's strong, right? So anything less than 0.3 is going to be weak. Between 0.3 and 0.5, even on the negative end, right, would be considered moderate. And then anything over 0.5 is considered strong, right? The difference is kind of how we interpret the effect size versus the correlation. The correlation is the strength and the direction of a relationship, whereas the effect size, right, is the size of the difference that you're attempting to find, right? And so maybe I'll highlight that. Where was it here? The effect size is the size of the difference, right? So even though it is the correlation, depending on what we're talking about, right, we're going to think of them as different things. And so if you're asked to define the effect size, then this is what it would be. Okay? The thing is that if you have a large effect size, meaning you suspect that there's a big difference between these two groups, you're not going to need very large sample sizes to detect that, right? Because those differences are going to emerge almost immediately, right? Whereas if you've got a very small effect size, right, these are very minute differences that you're trying to pick up on, you're going to need larger sample sizes to capture that, right, for those differences to kind of emerge. Okay? So that's what this blurb is all about. But also, to calculate the sample size, we said that, okay, we're going to incorporate three things, right? The effect size, the power, and the alpha. So I'll scroll up so you can see. You got it in front of you anyways. The effect size, right? How big of a difference are we expecting to see here? Is it small? Is it big? That's going to determine how big of a sample size we need. We also need to think about the power. The power is this like kind of weird thing that we can't really grasp at, right? And so we just say, oh, we have 80% power, or we want 80% power. But it doesn't really, there's no calculation for it that we've talked about, right? And so we just need to think about the power. And then the alpha, remember, is the probability of making a type 1 error when you reject H0 when you shouldn't have, right? Going back to that table. And the power is 1 minus beta, 1 minus the probability of type 2 error. So they're all intertwined. Okay. Any questions from that section? Just a brief little section. And let's move on to the chi-squareds. We didn't do chi-squareds, we did t-tests and then chi-squareds, but I've got them in order of the chapters, right? And so the chi-squared, you guys seem to like, which I'm kind of like, oh, interesting, interesting. Maybe it's because it's the second hypothesis test that we talked about, and so I feel like you had a little bit more of a handle on it, right? But so the chi-squared test is if you've got nominal or ordinal level variables, what does that mean? That means that you have categorical variables, right? And so we have to have categorical variables. Categorical variables. Because you guys read those research studies and we talked about it, right? But that to make a chi-squared, we have to have a table of all our categories against our other categories, right? Our two variables are in a table, in a two-way table. And then we said, we're gonna focus on 2x2 tables, right? Where we have a variable with two outcomes or two categories and another variable with two categories, right? And so here, these are presented in a two-way table. We can absolutely have more than two categories in each variable, right? But we just said we're going to focus on those ones with just two. Your internet connection is unstable. Thanks. Okay. Hopefully it sticks around. Right, and so we present these in a two-way table, and then we've got counts in each cell. Right. For our null hypothesis, for a chi-squared, it's going to be that there's no association between these two groups, right? Or these two groups or variables. Right. The groups in general, but the variables. Right, so for chi-squared, we're talking about associations. We calculated a chi-squared and you did it for a bonus mark on test 2. It's not going to be on this one. It's not going to be on the final, right? So I'm going to leave it here. Maybe I won't. Mindy I can't. You're going to have to find your degrees of freedom, right? And then, so your degrees of freedom is on your formula sheet. It's the number of rows minus 1 times the number of columns minus 1. And so because we're only going to consider 2x2 tables, well, 2 minus 1 times 2 minus 1 is 1 times 1, which is 1. 1, 1, 1, 1, 1. Right. So we will have 1 degree of freedom, but it's very possible to have more than 1 degree of freedom depending on how many categories you have in each variable. So then after setting up your 2x2 table or just in general two-way table, two-way table, not necessarily a 2x2, right? For us, because we were only using 2x2 tables. You need to find the row totals, the column totals, and the grand totals. And then what we do is we find the expected frequency in each cell, right? So what that does is it says, okay, assuming that these are all there's no association here and they're distributed just randomly, then we would expect to see these counts, okay? Which is going to be the row total times the column total divided by the grand total. We're not going to do it, so I'm not going to spend any time on it. Then we can calculate our chi-squared value. Our chi-squared value is, and I just use kind of lazy math notation, it's the sum of the observed minus the expected squared over the expected. Here, once you have your calculated chi-squared, right? So, for example, on quiz 2, there was a question that said, okay, you found a chi-squared, I want to say of 2.7, something like that. Using this chi-squared value, what's your conclusion, right? The hiccup there is that, okay, well, to determine what to do with a chi-squared value, we need to know, okay, how many degrees of freedom do I have, right? And so the correct answer there was unable to determine without the degrees of freedom, because there was no mention of there were this many rows and this many columns to help you find the degrees of freedom, which is what you would need in order to deal with that, right? So if you have a chi-squared value, then the only way that you could know how to deal with that and find a p-value is if you have the degrees of freedom, right? So your next step would be, okay, what are my degrees of freedom? Then you would go to the table, figure it out. Or use software, and I'll show you some output in a second. So the assumptions for chi-squared is that we have to have nominal or ordinal level variables, right? So we have to have categorical variables. Here's where we kind of veer off depending on if we've met these conditions or not, right? So we're starting off and we're saying we're going to do a chi-squared test. I have to make sure that all cells have an observed and technically expected, but we'll stick to observed. I'll put and expected in brackets because we didn't take it that far. It's true, but we didn't go there. So we have to have an observed value greater than or equal to 5 in each of the cells, right? And so you had a question on quiz 2 that said, well, one of these cells actually only had a count of 1 or 2 or something like that, right? If that's the case, then you can't use chi-squared anymore, right? So remember, we set out on this chi-squared path. Our first checking point is, do we have all cells that have more than 5, right? Each cell has to have more than 5. If they don't, that's fine. We can't do a chi-squared, but we can use the Fisher's exact test instead. Okay. If it passes that check-in point, right, we have more than 5 in each cell, great. Then we move on. Do we have more than, so do we have between 5 and 10, right? So basically, do we have less than 10 in any of these cells? More than 5, but less than 10. If we do, right, we can do the chi-squared, but we have to apply Yates continuity correction, which we didn't talk about besides, okay, well, this is when you would use it, right? We didn't talk about what it is or anything like that, right? But you would do a chi-squared with a Yates continuity correction, right? Because just to correct for those small sample sizes. So the last thing that you're going to check is, okay, if I want to do a chi-squared, well, then my 2 variables that I'm analyzing, they have to be independent. If they're not independent, husband and wives, for example, right? Sister, brother. Why are these all male, female part? I don't know. But anyways, those would be dependent, right? And so if you don't have independent variables, you should use the McNamara test instead of the chi-squared. Right? And so all these tests are just kind of instead of a chi-squared or on top of a chi-squared. Once you've checked all these, right, basically, do you have more than 10 in each cell, right? Are your variables independent? Do you have categorical data? Yeah. Then you can do a chi-squared and everything's fine, which is usually the case, right? We've just got these special kind of detours that we make. Okay. We didn't use Excel to do a chi-squared because Excel isn't very good. Period. End of sentence. No, it's fine, but bless you. But for analyses like these, it's not very good at doing chi-squared tests, for example. And so this is from SPSS or some other software. Just want to give it to you so you've seen it. Yeah. The chi-squared test, what it does is it gives you the Pearson chi-squared, which is your regular chi-squared. It also does the continuity correction. It gives you Fisher's exact test, and then linear by linear association, I don't know what that is, and then the number of valid cases, that's garbage. So, no, it's just saying your sample size was 80. But, so it gives you these three, potentially four, but we didn't talk about this one, right? And it's your job to pick which one is appropriate, right? Chi-squared, Yates continuity correction, or Fisher's exact test, right? So you have to look at your data and decide, well, do I have a cell that has less than 5, right? Then I have to use this row. Do I have to use Yates continuity correction? Because I have cells that are between 5 and 10. Then I'd use this row. Am I good to go with just the chi-squared? Then I'd use this row. Your p-values are all these guys, right? So depending on, I didn't do a very good job highlighting those, but for a chi-squared and Yates continuity correction is a chi-squared with a little extra, right? And so it only gives you a two-sided p-value, and that just stems from the shape of the chi-squared, which we don't have to worry about. Okay? But it's going to be a two-sided p-value, and so these are your p-values. Based off of these are huge, right? Would you reject H0? No. All right. And so here, these are our two-sided p-values. You won't have to divide those by 2 or anything, right? You can just use those p-values that it gives you. Fisher's exact test, it gives you the one-sided or the two-sided p-value, right? So you get to choose, but you're probably just going to use the two-sided, right? Because that's our default. Say there is a question that incorporates this. It might say something like, if you have done a Fisher's exact test, what would your conclusion be? Well, if we're assuming we have a two-sided p-value, even with a one-sided, it doesn't actually matter. Well, for Fisher's exact test, I don't have enough evidence to reject H0 because these are my p-values, right? 0.642 is huge. It's definitely not less than 0.05. So I don't have enough evidence to reject H0, right? Regardless, all of these p-values, well, one, they're going to be very similar because they're doing essentially the same thing. But two, right, all of these, we would not be able to reject H0 because the p-values are so huge.
So you wouldn't divide them by 2?
No.
Why not?
Just leave them. Just because of the shape of the chi-squared distribution, but it doesn't.
In what instance did we divide it by 2? Because there was one, right?
As a rule, if you're looking at output, just use the p-value that it gives you. So you don't have to worry about that. That was me being picky. So as a rule, just use the p-value that it gives you. All right. So don't worry about that. Good. Then I'm happy. Any questions about chi-squareds. Oh. T-tests. We hardly talked about one sample t-tests, barely even touched on it, right? And so mostly because we would use a one sample t-test if we wanted to compare the mean of our sample to some hypothesized value, right? Is the mean less than 30? Is the mean greater than 4? Right? Weird things like that. Where did those numbers come from? Probably some other sample. And so then you would be better off comparing samples, right? So, so we don't really use one sample t-test. It happens, but especially in this course, we focused on two sample t-tests. Two sample t-tests, you can either have two independent samples or two dependent samples. We'll talk about two independent samples first. If you've got independent samples, well, that means that there's no way to link an observation in group 1 to an observation in group 2, right? Meaning they're independent. And so if you've collected a sample of males and a sample of females, for example, if there was a way to say that, well, this one's married to this one, this one's married to this one, and you're able to pair them, that would be a dependent sample, or those are dependent samples. But if you're just saying, oh, here's a random group of males and here's a random group of females, there's no way to say that this male goes with this male goes with this female, right? And so those are independent groups, right? And so you just want to keep track, okay, are these groups going to be independent or dependent? Your null hypothesis for two independent samples, t-tests always have to do with the mean, right? And so what does that mean? The underlying assumption is that we have numerical data, right? And so we have to talk about the mean, how it compares to the mean. So the mean of population 1 is not significantly different, right? So no difference from the mean of population 2. Not to be confused with the dependent variable. The dependent variable is the thing that we're measuring. So if we're talking about the mean height of group 1 is not significantly different from the mean height of group 2, right? Our dependent variable would be the height, right? Whereas the group 1, group 2 would be our independent variable. So it gets a little dicey just because we've got dependent variables and independent variables in our independent and dependent t-tests. The dependent variable is also called the outcome variable. And of course, for a t-test, we're only able to compare the means of two groups, right? If we wanted to compare more than two groups, or even two groups if you wanted to, you could use an Anova, right? An Anova compares the means between two or more groups. But usually we'd only apply it for 3 or more, but you can use it for 2 or more. The thing about our independent t-test or our independent samples t-test is that it's going to change depending on if we can assume equal variances or not. So if you're doing a t-test, you're doing a hypothesis test, but we have to check if we can assume equal variances or not. right? So we're doing a hypothesis test within our hypothesis test. Levine's test, right? We have to run, and I think this is probably where we were thinking about, but just use the output that it gives you. I think, yeah, for Levine's, yeah. So just, we've got the output that I'll show you guys. But for Levine's test, just use the p-value that it gives you. You don't have to worry about it. Levine's test, like I said, is a hypothesis test, and it tests the hypothesis that the variance of group 1 is not significantly different from the variance of group 2. Meaning, if we don't reject H0, we can assume equal variances. If we reject H0, we cannot assume equal variances, and so that's going to dictate what type of t-test we're running. So, and of course, we're just going to use output, or I'll just give you the p-value, and you need to know what to do with that. I'm going to zip ahead here because I've got this printout, which is the same as the one, I don't know why it says Lewin's. That must have auto-corrected. Should be Levine's. Not sure what happened. So you've seen this table before, right? And so this is SPSS output in Excel, right? We had to do the Levine's test, and then we can do our t-test. Here, it's combined the two, right? So we've got Levine's test gives us an F, and the significance, which is your p-value, right? The sig is always your p-value. Gives us our F, and our p-value, we're going to ignore whether it's one-sided, two-sided, whatever. We're just going to use a p-value of 0.049. If the p-value is 0.049, that's less than 0.05. So we can reject H0, which means, okay, if we're rejecting H0, we cannot assume equal variances. And so that tells us which of these rows we're going to use, right? If we're not assuming equal variances, then I think the question that you had on quiz 2 asked you which t should you be using, this one or this one. We would have to use this one, right? So it's assuming that you know what to do here. And then, so often with these outputs, what you'll notice is that it gives you everything that it can possibly do. And then it's our job to figure out, okay, well, which one should I be using? This one or this one? Well, based off of this, we cannot assume equal variances, so I should use this. Maybe I'll put a little note here. Can't assume equal variances, right? Which means that we're going to be working in the bottom row. Yeah. If we're comparing the means of two groups, but these two groups are dependent, right? Often, if we've made two measurements on the same subject, right, in a pre-post score scenario, or if we're talking about siblings or married couples, those are kind of common paired situations, right? Then we have these two dependent samples. And our null hypothesis changes a little bit, right? Because we have to take into account the pairing. So now we're talking about the mean difference between these two groups is not significantly different from 0, right? It's not going to come up, so don't worry too much about it on here for completeness. The dependent variable, again, it has to behave the same way as for just two independent samples, right? So nothing changes between independent samples and dependent samples for t-tests. It's just how are the samples related to each other. Okay. Any questions? On to Anova. Anova is the analysis of variance, and the name is kind of misleading. It incorporates the variances, but for us, kind of face value, how do we use it? It's when we're comparing the means from a single dependent variable among two or more groups, right? And so we're still comparing the means among two or more groups, right? Remember, Anova only tells you if there is a difference between any of the groups. It doesn't tell you which one, right? And so it'll only detect a difference in general, and then it's our job to dive in and say, oh, it's probably here, test it using t-tests, right? We use these pairwise t-tests. A repeat measures Anova is very similar to the dependent t-test, right? The dependent samples t-test, in the sense that, okay, now we've got these measurements over time, right? But maybe over more than 2 time points, right? So now you've got more than 3 or more than 2 time points. And so you're examining a change over time for repeat measures. And so it just has to incorporate that, okay, well, I've actually made a measurement on the same individual over multiple times. And Anova gives you an F ratio, as we'll see down here in the output. And the F ratio, the closer it is to 1, right, the more the same these groups are, right, the means of these groups are. And so as your F ratio gets larger, you're more likely to reject the null hypothesis, right? Just the same way that a chi-squared and a t and a z and whatever else we've talked about, right? These F ratios behave the same way. As they get larger, we're more likely to reject the null hypothesis. So if we look at this output, it's got the between groups, within groups, blah, 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 blah. What we're focusing on here is it gives us our F ratio, which is huge, 72, right? And so our sig, which is our p-value, is approximately 0. So our sig in all these outputs is our p-value. .000 is approximately 0. But it's not 0. It's approximately 0. The problem is that no probability, remember the p-value is a probability. The probability is never going to be 0. That's just never going to happen. Because there's always room in the tails. These tails go to infinity and negative infinity. And so there's always a little bit of room for things to happen, right? And so we can never say that a probability is 0, but approximately 0, right? Based off of this, if you've got a p-value that's approximately 0, you can reject H0, right? If you're doing an Anova like we are here, rejecting H0 means that there is a significant difference in the means among the groups, right? At least one of these means is not like the other. Doesn't tell us which one, right? But at least one of these is going to be different. Carryover effects, right, are usually a concern for repeat measures testing, right? And so you've got, a group of patients, and you give them drug A for 3 months, and then you kind of let them sit for a little bit. They don't get any drugs, and then you give them drug B for some amount of time, right? And then you give them drug C for some amount of time. We don't know if those drugs are still going to be having an effect as you move through the drugs, right? So once you get to drug C, the effects of drug A might still be happening, right? And so that's when that's a major concern. And those are called carryover effects, right? Just carrying over from the previous treatment. And it can happen in a regular ANOVA or any testing, but it's just a concern for repeat measures because we are repeating measurements on the same subjects, right? So then it's a problem. Whew. Questions, comments, concerns? Correlation. That's where we ended off last day. There's nothing really to it, right? Except it's a numerical measure of the strength and the direction of our relationship. And so we said, okay, correlation goes between -1 and +1, where the negative is just an indication of if we have a positive or a negative relationship. And so we've got these down here. And so if you have a positive relationship, then things are going up, 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 up. And so you've got here for a positive relationship, it would look something like this, right? You've got this kind of, if you fit a line through it just to show the direction in general, right? This would be a positive relationship. Whereas if you've got something that looks like this, whereas one is increasing, the other is decreasing, you've got a negative relationship. And you'll have to, so it'll give you a blurb and say, oh, as this one is increasing, this one's decreasing, what type of relationship do you have, right? If one's increasing and the other is decreasing, you have a negative relationship, right? But if they're moving together, you have a positive relationship. You can do, kind of skipping back to up here, we can do hypothesis testing with correlations. We didn't really do any, but you can. And depending on what type of data you have, you can either use Pearson's R or Spearman's Rho, and we'll talk more about them here, or which one's appropriate when. But it was also last week, so kind of fresh. But our null hypothesis is that there's going to be no association or relationship, whichever one you prefer, between these two variables, which is very similar to a chi-squared, right? There's no association between these things, and we decided that correlation is actually just kind of an extension of chi-squared. The strength of the relationship is just how closely things are moving together, right? If your dots, if you're looking at a scatter plot and these dots are forming this very distinct pattern, then you've got a strong relationship. If there's kind of random scatter everywhere, you've got a weak relationship. But your correlation, right, we said is the same as the effect size. And so, of course, we have the same groupings, right? A correlation that's less than 0.3, positive or negative, right, is going to be weak. Between 0.3 and 0.5, moderate. And then anything larger than 0.5 on either end, right, positive or negative, is going to be considered strong. Okay. Oh, I do want to highlight one thing. because the correlation is a numerical measure of the direction of the strength of the relationship between two variables in one sample. Okay, so these things should be from the same sample, which is not necessarily obvious, so that's why I'm pointing it out. Oof. I got nothing. A sweater, no. It's like, should use the whiteboard eraser. Oops. So we've got some options here, right? We said, okay, depending on what type of data we have, right, we'll be able to pick which correlation coefficient we should be using. For Pearson's correlation coefficient, we have to have a relationship between two variables that are normally distributed. What that translates to is that we have a linear relationship. So R is only appropriate if you're looking at the relationship between two variables from one sample that have a linear relationship. Whereas Spearman's rho is just a Greek letter, and I didn't bother putting it in here, but rho just looks like this. Not that you need to know that, but basically, if you don't have a linear relationship, you're going to use Spearman's rho. But our go-to is going to be Pearson's correlation coefficient, R. And we can use lowercase r or capital R. Those are used interchangeably. And then Spearman's rho, we just use rho. If we've calculated R squared, right, that's our percentage of variance. And so as soon as you see percentage of variance, right, or percentage of variability, okay, you're going to think R squared. That's your correlation squared. Okay. So as soon as you see something like percentage of variability, you're going to think R squared. That's your correlation squared. So it's your R squared. But then because it's a percentage, you're going to have to multiply it by 100 to get a percentage. And finally, with not a whole ton of time to spare, homoscedasticity is not going to come up on the final, but I thought I'd throw it on here just in case. But it's the equal spread. So one of the assumptions, right, for a correlation is that we have homoscedasticity, meaning we have equal spread around this kind of imaginary line of best fit. Any questions at all about the final exam? Before you go, my husband is flying in on Thursday, so I'm not ideally going to be here on Friday or on Monday. So just keep that in mind, but I will be here all day on Tuesday, and of course all day on Wednesday. And if it's urgent, just email me, okay? Or text me is probably better.
Thank you.
Oh, well, hey, this isn't our last time. This is not our last, I'm not ready. Don't forget about bonus mark day.
It's the week after the exam.
Yeah.
Okay, so remember that.
Yeah.
So you said you don't do chi-squares.
You don't have to calculate any chi-squares.
But we have to know about it.
Yeah.
Okay.
So just like what are they? If I give you something, right, what are you gonna do with it?
Is that the same with like tests? Like we go into tests. Is there any that we have they have to like in the calculator. So it's
There's,
all-
I think, 2 percentages, the 68, yeah, just like, if this many passed and this many failed, what percentage failed?
Oh,
Yeah, so that's fine. And then, so that's, I use my calculator for those two,
but no mean test, no variance test, no.
besides looking at output like we just did.
You need to know what the output, you don't have to find it.
Exactly.
Okay.
Yeah. And then the other thing that I used my calculator for was calculating R squared and the 68, 95, 99.7. It's just the correlation squared.
And then.
And I would give you the correlation. Yeah.
All right.
Nice. All right.